that interact with the Higgs. Here the sum on I sums over all of these individual contributions. And the place where the Higgs coupling comes in specifically, where's my chalk, is in these mi squareds. So mi squared here is, just move this a bit, is the field-dependent mass. And what I mean by this, and okay, so sorry, I'm going to write below the line. So the mi is mi of phi. And for example, for the top quark, mi squared of phi is just the top Yukawa squared phi squared. So in other words, the mass squared of the top quark is just the top Yukawa times the Higgs of. So this is the familiar top mass. And another example would be the W. And for the W, mi squared of 5 is just g squared over 2 phi squared, where g is the SU2 coupling. And okay, my apologies. I'm one of these perverts who uses a normalization where the standard Higgs value would correspond to 174 instead of 246. So I guess Christoph is gone. Fortunately, he can't shame me. Okay, so anyway, back to these loop functions. The most important contributions to the loop functions come from the things that interact most strongly with the Higgs. So specifically, we're interested in stuff that couples. We're interested in stuff that couples strongly to the Higgs, and the stuff that couples most strongly to the Higgs in the standard model are essentially the W and Z vector bosons and the top quark, because these are the things with kind of order 1 couplings. If I was to think about a bobbin quark or a strange quark or something, the corresponding Yukawa coupling would be really tiny, and you wouldn't get much effect. So just keep in mind that the most important corrections are going to come from the from things like tops and W's and Z's, and maybe particles beyond the standard model that interact strongly with the standard model. So now these loop functions, I gave you a full expression for the loop function yesterday, but you can get by pretty well for the most part using one of two asymptotic forms. So there's a high temperature asymptotic form and a low temperature asymptotic form, where high and low temperature refers to temperature relative to the mass at the particular point in field space you're looking at. So for a given phi, you have some corresponding m squared that depends on phi, and you compare this mass squared to the temperature. So the low temperature expansion corresponding to large X, corresponding to mi squared over t squared larger than about 2, gets a Boltzmann suppression. So this is the same Boltzmann suppression that you always get from thermal effects. This shouldn't be too surprising, but this means that these contributions are very, very strongly suppressed as your mass gets bigger than the temperature. So we can basically just dump stuff with very big masses. On the other hand, for smaller x, and it turns out that this asymptotic form and this asymptotic form both work pretty well up to this level of expansion, up to or below about x equals 2. So for x less than equal to about 2, expanding in this so-called high temperature expansion works pretty well numerically. So there are various contributions. Roughly, this is an expansion in something that looks like x over pi. So x over pi is slightly less than 1. But I'm going to come back to the specific form. But just before I go on, I'm going to put a nice yellow thing around this term here. So this term, for electroweak baryogenesis, is going to be really, really important. And it's a slightly funny form, a slightly funny term. If I think about, this is an x cubed thing, and I'm putting this in as a function of x squared, where x squared corresponds to m squared over t squared, I can think of this x cubed as being like x squared to the 3/2 power. So in this sense, it's kind of funny and it's non-analytic. There's kind of a nice story behind it, corresponding to the infrared structure of the thermal theory, but I won't get too much into it. But I want to emphasize that this x cubed piece is really important, and you only have an x cubed piece for the bosons, not the fermions. So I'm going to come back to this and emphasize it in a second. So we want to do electroweak baryogenesis. And if you remember the cartoon of electroweak baryogenesis I drew yesterday, electroweak baryogenesis has all kinds of interesting stuff happening near bubble walls. And these bubbles correspond to bubbles of electroweak broken phase expanding within the surrounding plasma of electroweak symmetric phase. So in other words, I have some region where my Higgs expectation value is non-zero, and this acts like a bubble, and it's expanding out within a surrounding phase where the Higgs expectation value is 0. And the interesting stuff for electroweak baryogenesis is going to happen sort of just outside these bubble walls. So yesterday for the standard model, I wrote down the standard model effective potential, keeping only the leading high temperature correction to it. So the leading high temperature correction, and by high temperature it means small x, the leading non-trivial high temperature correction to the standard model effective potential is kind of roughly a tree level potential, possibly with normalized parameters that absorb the stuff in here, plus the leading term in this expansion is these x squared pieces. And putting in the x squared pieces, we found that you get a thermal correction to the Higgs quadratic term that turns it from negative to positive, and this moves your potential and effectively restores the electroweak quote-unquote symmetry at high temperatures. Now, the potential we wrote down yesterday doesn't quite do what we want for electroweak baryogenesis. So we want specifically for electroweak baryogenesis these bubbles, and to get these bubbles, you need a first-order phase transition. So there are more rigorous definitions of a first-order phase transition than I'm going to give, but for our purposes, a first-order phase transition is one where the effective potential at some so-called critical temperature, let me find some nice red chalk. A first-order phase transition is one for which at some temperature, the potential has two degenerate vacua, or two degenerate minima, one at 0 and one away from 0. So I'm going to call this point phi c, and I'm going to call this the effective temperature at temperature Tc. Now, at temperatures higher than Tc, the effective potential may have a little dip in it, but will only have typically a global minimum at the origin. So this is T greater than Tc. And what we want our potential to do at temperatures, lower temperatures than the so-called critical temperature, is just go to the usual Higgs potential. So for T goes to 0, I want to get back to something that looks like my usual Higgs potential, where my origin is unstable, and I have my only global minimum lies away from the origin, corresponding to broken electroweak symmetry. So this is the kind of potential I want for a first-order phase transition. And the reason I want this kind of potential is, suppose I start with a system at very high temperature. If I start with a system at very high temperature and I cool down fairly quickly, if I'm cooling down fairly quickly, you can think of this as sort of a quantum mechanical instantaneous approximation. I'm going to start by living in this vacuum state here. And as long as the system doesn't cool really, really slowly, as the temperature evolves, my effective potential is going to evolve from this, where the only vacuum state's here, to this so-called critical temperature form of the effective potential. And now, when the potential looks like this, I'm going to be stuck here. So I started here, I'm going to be stuck here, and I'm going to remain stuck here until I have time to tunnel from here out. And typically, the tunneling won't start until the temperature cools a little bit more, and the temperature cools a little bit below the critical temperature, such that the global minimum is slightly lower than this minimum at the origin where I start stuck in. And this is where bubbles come in that when I tunnel from here to here, I don't just tunnel everywhere in the universe all at once. This has to happen somewhat causally. And the way the tunneling works, and the tunneling can either go through actual quantum tunneling or through a thermal fluctuation, is one way or another, I transition from here to the deeper global minimum. I'm kind of running out of chalk colors, but I transition from here to the deeper global minimum. And the way this transition takes place is through the nucleation of a bubble of broken phase within the surrounding plasma of symmetric phase. So the idea is that through a tunneling event, I nucleate a bubble of finite size. So I nucleate locally with a bubble of finite size. And as long as this bubble is bigger, the gain I get in free energy by going to a deeper part of the effective potential, means that it's thermodynamically favorable for this bubble to expand. So I nucleate a bubble of larger than so-called critical size. And when I do that, it's thermodynamically favorable to expand. So I nucleate a bubble, and the bubble expands. And now, in general, I don't just nucleate one bubble. I nucleate a bunch of different bubbles in different locations. And these bubbles all expand, and eventually they smash into each other and coalesce. And eventually, with enough bubbles and enough expansion, and so on and so forth, everything comes together. And at the end of the day, I end up filling the whole universe with a broken phase. So this is a first-order electroweak phase transition. It's a first-order electroweak phase transition, and because it's first-order, I get these bubbles. The bubbles are a necessary ingredient for electroweak baryogenesis, and to see how bubbles come about, we're going to see that this term plays a very important role. Okay, so if I go back and look at my effective potential, very roughly, I either have, I have a bunch of contributions. I have the low temperature contributions, the high temperature contributions and the low temperature contributions. I can more or less ignore the low temperature contributions because they're both suppressed. So let's look at the effective potential corrected by these high temperature contributions in sort of a schematic way. And I'm going to keep the high temperature contributions up to essentially quartic order in X. And my very schematic form of the full thermally corrected effective potential is something that looks like this. So this form of the thermally corrected effective potential looks very much like what I wrote down for the standard model yesterday. The only difference is that yesterday, what I wrote down only kept up to quadratic order in this X expansion, in this high energy X expansion. So for now, let's ignore this. And this lambda bar is, in the standard model, pretty close to lambda, where lambda is the Higgs coordinate coupling. So let's just think of this as the usual standard Higgs coordinate coupling. And let's ignore this piece for now, and just think about this part. So in this notation, d times t squared corresponds essentially with the minus mu squared that you have in the standard Higgs potential. And this means that if I look at this piece and this piece at zero temperature, this t squared goes to 0, and this t0 is just some constant. And that means that I get a negative coefficient for phi squared. And that means that at t equals to 0, my potential looks the way I want it to. My potential just looks like a standard Higgs potential with an unstable origin and some global minimum away from it, where the coordinate coupling is stabilizing me at large field values. But now if I go back and put this piece in, this is the piece that can make my phase transition strongly first order. So again, if I ignore this, what happens is my origin, because of this piece, is either stable or it's unstable. So if t is less than t0, my origin's unstable, and my potential looks like this. If t is greater than t0, then the origin is convex, and my potential just looks like this, if I ignore the cubic term. The cubic term is what drives, in this picture, is what drives the phase transition to be first order. So what the cubic term can do is, because the cubic term is negative, if I'm in a regime where this term is still positive, if this term is still positive, it dominates near the origin, and that means that near the origin, I'm going to have something that's going to be stable, at least locally. But then as I go further out in field space, the E cubed term can kick in, and it's going to turn my potential over and possibly drive it to be as deep as I had before. And then eventually this piece kicks in at even larger field values and stabilizes me asymptotically. So this cubic term is what I need to, is a thing that's making the phase transition potentially first order. So you can... Yes. Yeah. So just the way I've set it up, this my field variable can be positive. So I swept a bunch of stuff onto the rug, but it's effectively real and positive. Okay, so this is the piece I want to concentrate on. And in fact, if I use my vast algebraic skills, even I am able to minimize this potential. And if I've done it right, the answer for the local extrema plus or minus so my local extrema looks something like this. Okay, again, this is maybe not so illuminating. I'm just showing off my powerful skills of algebra. What I'm really concerned with is looking for a critical temperature. And you can show that as long as you have this cubic term, and the cubic term takes this form, you do get a critical temperature. And the critical temperature ends up having a ratio of the field value, phi c, here. So this is phi c. This is what I call phi c, the value of the field at the local minimum at the critical temperature, where this non-zero minimum is degenerate with the origin. Phi c over Tc, in my perverted choice of lambda normalization, is just E over lambda bar. Okay, again, this is just some algebra that you fiddle around. And we're going to see in a little bit that specifically the condition for successful electroweak baryogenesis isn't just getting bubbles. You need, in some sense, this first order phase transition to be strong. And what strong means in the context of electroweak baryogenesis is roughly that this ratio should be larger than about 1. So I'll come back to this later. But kind of intuitively, a strongly first order phase transition is one where this minimum is separated a lot from the origin. And by separated a lot from the origin, in dimensionless grounds corresponds to the size of this separation being larger than about the temperature. So this condition 1 is often called the condition for a strong or strongly first order electroweak phase transition. Okay. So very good. Now we can go and study our standard model and see what it gives. And it turns out that the standard model, at least at this level of analysis, looks like it does give you a first order phase transition. But if you put in if you put in the values of E and lambda corresponding to the standard model potential and the standard model contributions, the phase transition is only strongly first order. It turns out for values of the Higgs mass less than something like 50 GeV. So obviously we know that the Higgs is heavier than 50 GeV. So the standard model fails for electroweak baryogenesis because it doesn't give a strongly first order electroweak phase transition. So in fact, it turns out that the standard model with 125 GeV Higgs doesn't even give a first order phase transition at all. So this isn't obvious from this picture, where it seems like whenever I have a non-zero E, I always get a first order phase transition. And the reason the standard model doesn't quite work, it doesn't even give you a first order phase transition, is related to extra thermal corrections that I'll get to in a minute. But in any case, the standard model doesn't work for electroweak baryogenesis because for the observed Higgs mass, we don't get a first order phase transition at all. So this is motivation for new physics beyond the standard model. And what we want from the new physics beyond the standard model is effectively something like a cubic term in the potential There's another approach where instead of a cubic term, you get something like a phi to the sixth term. Lian Tao spoke about this yesterday. I'm going to concentrate on getting a cubic term. So there are two primary approaches to making the phase transition first order by going beyond the standard model. The first is to add new particles that couple to the Higgs that contribute in loops, and that generate essentially a larger effective value of this E coefficient through their loop contributions in the effective potential. And the second approach is just to couple new scalar fields to the Higgs that also get vacuum expectation values such that mixing with the Higgs generates effectively cubic terms. So let me start off with a loop approach for new physics beyond the standard model to contribute to the E coefficient. So if I look at the JB and the JF doesn't have any cubic term. And it's a cubic term that I want to make bigger to enhance the phi c over Tc to get a strongly first order phase transition. So this means that the new stuff I put in should be a boson. And the size of what I put in contributing to this is going to be bigger the larger the thing couples to the Higgs. So here's a simple toy model. So I'll call it model 1. So a simple toy model is to add a new scalar field X with, I'll make it a complex scalar, and it'll have some mass term, mx squared. And I'm going to give it, this piece I'm not going to use for the phase transition, but it's going to just stabilize the X potential. And the third piece I'm going to put in is a so-called Hex Portal Interaction. And let me just see. Actually, sorry, I called this K. And I'm going to call this Q. So this new interaction is called a Hex Portal Interaction. It's renormalizable. And I'm allowed to write it down. It's gauge invariant. Okay, let me emphasize that this is a Q, not a phi. The Q is just some coupling. I'll try to make a little squiggly thing to differentiate it from the phi. This new Higgs portal coupling can be added no matter what the gauge charge of X. So X can have any standard model gauge charge I possibly want. It might be charged under some new vector gauge groups. Who cares? I can always write this down. There's nothing stopping me based on gauge invariance. Now, if I put this X particle and I look at its field-dependent mass, I get mx squared of phi in the Higgs background equal to mx squared plus q phi squared. So for now, I'm going to assume that the X particle, this X scalar, doesn't get any kind of vacuum expectation value. And I can ensure this. I can ensure this with either a big positive q or a positive mx squared. So I take this mx squared of this form, and I plug it in to my my JB function here, and I look at its correction to the effective potential. And specifically, I want to look at its correction to the effective potential corresponding to the E term. And what I get is a correction to the effective potential, or one of many corrections to the effective potential, but the correction I care about turns out to be minus t over 12 pi times gx. Gx is the number of degrees of freedom of the X particle. So if X, let's say, has colors or something, or dark colors or whatever, the X can be some big number. And finally, I have an X cubed term. So X cubed is I take mass squared over temperature squared, and I plug it in here, and I take the, well, I take the 3/2 power. So in other words, this term ends up coming like m squared plus q phi squared to the 3/2. So this is the contribution to the effective potential that is possibly nice for what I want to do. So I can look at two limits. If I take the limit where this mx squared parameter is really, really big, I don't get what I want. So if mx squared is really, really big, I can expand out in powers of, I can factor out the mx squared and expand the rest of this piece in powers of essentially q phi squared over mx squared. And for large mx squared, those higher order corrections are going to be small. So if mx squared is very big, I don't get the nice cubic term that I wanted. On the other hand, if mx squared goes to 0, this thing turns into a genuine cubic piece. So they're kind of roughly two interesting limits. I'm going to concentrate on the limit where mx squared becomes small. So when mx squared becomes small, and okay, sorry about this. I'm just going to write down here. I get a minus t over 12 pi gx q to the 3/2 phi cubed, and I identify pi here, and I identify this with the delta E correction I wanted. So I can make, okay, sorry, I guess people can't see that. Okay, so all I'm doing is taking this equal to 0 and expanding out, and I get a correction to the E coefficient given by essentially gx over 12 pi q to the 3/2, because as mx squared goes to 0, this becomes a genuine cubic piece. So it turns out that this can do the job. This can do the job provided mx squared is pretty small, and this Q coupling is pretty big. Now, one particular example of this that was studied a lot is the MSSM, the minimal supersymmetric standard model, where if you have a limit where one of the scalar quarks, one of the scalar top quarks, is very light, and its soft mass is essentially 0 or even negative, this Q coefficient ends up matching up with the top U coupling, so about 1. The X ends up being the scalar top, and I get a GX coefficient of 6, if I remember right. So this picture can drive a strongly first-order phase transition in the minimal supersymmetric standard model, provided I have a very light scalar top. Unfortunately, if I have a very light scalar top that couples in this order 1 way to the Higgs, I get big corrections to Higgs production and decay rates, because this new state couples in loops, and in particular, it couples in the loop that generates Higgs to glue. And this would, if you had such an object, it would give you a big enhancement in the Higgs in the Higgs production rate through gluon fusion that's now ruled out by data. On top of that, your light scalar top would also have to be so light that, assuming it has relatively standard decay channels, is already ruled out by quite a lot by direct LHC searches. So in any case, this story had been studied a lot within the MSSM, and it seemed promising, but it doesn't actually work because of LHC constraints. On the other hand, you can do this with, let's say, a singlet or a bunch of singlets, and these things are still pretty safe in terms of Higgs rates and direct searches. Now, having said that, this story also illustrates why electroweak baryogenesis is, on the one hand, challenging, but also nice. So the challenging part is it's hard to make electroweak baryogenesis work given current LHC data and constraints and other constraints. On the other hand, electroweak baryogenesis is really, really testable. So in contrast to something like leptogenesis, where all the new stuff can be at 10 to the 9 GeV, here the new stuff really has to live at the weak scale to have a big effect on the effective potential. And this means that the LHC gives you very strong constraints on proposals for electroweak baryogenesis. Okay. I'll just mention this in passing and not get too deeply into it. It turns out, just as a word of warning, it turns out that this thermal expansion is often not very good. So there are higher loop thermal effects. There are higher loop thermal effects beyond what I've included here that can change the result. And specifically, these higher loop thermal effects can be so bad that they can just mess up the whole perturbative expansion. In the context here, the leading contribution of these additional thermal effects corresponds to the fact that on top of this piece, I get a thermal contribution to the mass of this state. And the rule, roughly, for incorporating this in the effective potential, at least at the leading non-trivial order, is to add this thermal mass contribution that I'm going to call pi of t. And typically, at leading order, it goes like t squared times some large coupling, is to add this thing to this expression for mx squared in the effective potential, specifically in the cubic term. Now, this makes my life harder because this thermal mass correction it turns out to be positive. And now instead of having to deal with mx squared going to 0, I actually want mx squared plus this thermal mass correction combined to go to 0. But this thing's necessarily positive. So what you often have to do, not always, but often, if this thermal correction is big, is to combine this with this. In fact, you make this mx squared negative to cancel off the thermal correction at the temperatures you care about for the phase transition. So you get an effective cubic term by canceling this piece plus the extra thermal contribution that should be added to this cubic term here. So okay, I don't want to go too much more into this, but let me just say that even including this thermal correction, your perturbation theory is still pretty iffy. And in passing, this is also why the standard model of phase transition is not even first order at all, even though it might naively seem so because I do get a cubic term in the standard model. In the standard model, I get big thermal corrections specifically to the W and Z masses that contribute to the E term in the standard model. And these end up generating a phase transition that is not even first order for 125 GeV Higgs. So the really state-of-the-art thing to do, and okay, this is non-trivial, but the really state-of-the-art thing to do is essentially lattice simulations of the thermal field theory. Now, calculations based on this picture are useful and helpful in that they tell you what could potentially work. They give you a picture of what could potentially work. But to really get a precise value of phi c over Tc, to find in some appropriate way, you more or less need to do actually a proper non-perturbative study. Okay. Let me change gears now. So a second approach to getting a strongly first order phase transition is instead of trying to do everything with loops, let's just do it at tree level. So the tree level picture, or at least might naively seem easier, but it has its own challenges. So a very simple example of a tree level picture is, let me change my V0 actually, I'll just write this as a function of the Higgs. Let me add, instead of a new thing that contributes at loop level, let me add something that contributes, in fact, right at tree level. So a new thing at tree level, okay, actually, I guess I could have called this X as well, but I'm going to do this for just a regular gauge singlet. So I'm going to add a new gauge singlet that, in general, can get its own expectation value. And I have a modified tree-level effective potential that looks like this. And specifically, in the tree-level effective potential, I've got a cubic term involving the n field alone, and a cubic term involving n and 1 Higgs squared. So these kinds of terms rely either on a VEV for n, or n being a singlet. Now, the picture here is, suppose I get mixing between the Higgs and the n state, which is generically going to happen when I expand Higgs goes to phi plus h over root 2. Again, here's my perversion. This cross term is going to mix the physical Higgs with the n state. And I'm going to get some complicated mass matrix. But to take account of that mixing, what I can do is write what would be the Higgs expectation value and the n background expectation value. I can write this in some set of polar coordinates where I have some magnitude. So now I think of my field space as two-dimensional because everything's mixing. I have a two-dimensional tree-level potential. And I use a set of polar coordinates for my two-dimensional potential where I have a magnitude phi and then these angles alpha that correspond to a field-dependent mixing parameter. So if I take this expression and I plug it in here, I get cubic terms right at tree level already for my effective potential. And it turns out that if you fiddle with this and adjust your parameters and this and that, you can get strongly first-order phase transitions driven by tree-level effects. This can potentially work. is much less sensitive to thermal corrections because you're not driving it by loops. You're driving it by tree-level effects. The challenge here, though, is often, not always, but often, it could be very easy to get stuck in false vacua. In other words, you can get stuck in points in field space that aren't your global electroweak symmetry breaking minimum, but such that because you're separated by a tree-level barrier, instead of a loop-level barrier, that barrier is still present even at 0 temperature. And if the barrier is still present at 0 temperature and it's big enough, the tunneling rate from that other from that other local vacuum to our electroweak vacuum where we all want to live and be happy, turns out can be in some cases very, very long, and too long such that the phase transition never actually completes. So this is a challenging question, and it requires a calculation of nucleation rates of the bubbles. So that's the thing I want to get to next. We have these two approaches to getting a strongly first order phase transition. A third approach that can match to either of these two cases in the limit of a heavier mass is getting something like a phi to the 6th term. So Leontel spoke a little bit about that yesterday, and I won't say too much more. Question? No, well, so you're actually looking at a two-dimensional potential. So all I'm saying is now instead of working in a one-dimensional field space, you work in a two-dimensional field space, and yes, yeah. But within the two-dimensional field spaces, you can get barriers at tree level. Whereas you don't get a gauge invariance forbids a tree level barrier in the standard model. So you need to get it from these thermal loop corrections, for example. Okay, so let's say we've written down a brilliant theory of new physics beyond the standard model that gives us a strongly first order phase transition that's consistent with completing and gives us like phi c over Tc of sufficiently big. The next step in computing the final, in computing how much baryon density you get from this is to figure out how the transition actually completes. So I'm a bit low on time, so I'm just going to give you a sketch of how this works. So we have a potential that looks like this. So here's my phi, here's my v, and here's some temperature that I'm going to call the nucleation temperature that is slightly less than the critical temperature. So I've cooled below the critical temperature, and now this vacuum is slightly deeper than the origin, but I'm stuck here. So what I need to compute next is how fast I actually nucleate bubbles, either by thermal fluctuations or quantum tunneling. And roughly, the rate per unit volume for thermal, and again, I'm going to skip over this because I want to get to actually producing baryons, but the thermal rate typically goes like t to the 4th, e to the minus s3. So s3 is a three-dimensional Euclidean action. So the three-dimensional Euclidean action turns out to be just an integral d3x, where you look at time-independent field configurations that look like grad sky squared plus Vf of phi of t. And you evaluate this three-dimensional Euclidean action on a time-independent field that corresponds to a so-called bounce solution.
Does that need a factor of beta?
Oh, sure. Yeah, there should be a 1 over t here. Sorry. So this is your tunneling rate, and there's a bounce solution where, in Euclidean space, what you effectively do is you take your potential and you turn it upside down. So I take my potential, I turn it upside down, and it looks like this. And the bounce solution is a solution where I start here at asymptotic time infinity, and I roll down the hill, and then come up, and I stop at some point above here, and then I come back down and go back at asymptotic time equals minus infinity. Okay, actually I shouldn't call this time. It's actually in radius space, but okay. Okay, in any case, there's a so-called bound solution that you compute for the three-dimensional potential. And this gives you the nucleation rate for bubbles through thermal fluctuations. Now, there's also a tunneling rate, which in this case ends up going like mw4 e to the minus s4, where s4 is a Euclidean action in Euclidean four-dimensional action for a corresponding bound solution in the four-dimensional space. So again, I don't want to get too much into this, but this gives you the quantum tunneling probability. This gives you the thermal tunneling probability. And in both cases, your effective potential, your thermal effective potential plays an important role. Because the thermal effective potential is effectively determining the barrier to the tunneling, or the thermal fluctuation. In practice, the thermal piece tends to dominate. Actually, computing this stuff, though, is a serious pain in the neck. And fortunately, there's a very nice computer code, or set of computer codes to do it for you. So a very nice computer code to do this for you is called Cosmo Transitions. And for it, you essentially give it a thermal potential, or effective potential, and it computes these 3- and 4-dimensional Euclidean actions for you for the corresponding bound solution. This becomes especially non-trivial in multiple field dimensions. But in any case, Cosmo Transitions does a lot of this stuff very nicely for you. They're related codes. There's something called Vivacious that makes use of Cosmo Transitions. But for actually computing this stuff, there's a pretty well-established set of tools to do it. Okay, but in any case, we have a strongly first-order phase transition. We've nucleated bubbles. The bubbles are expanding. The next step is to actually make baryons. So I've had to do a lot of setup before actually making baryons, but we're now finally at the point where we can make baryons. But at least up to the point where we make baryons, we have to worry about this thermal effective potential, and this means we need to worry about thermal field theory. And all its beautiful and messy glory. Okay.
What is the free volume that's being used for computing this action? Does it just pick some sphere size?
Yeah, so this is this is per unit volume. So you compare it to Hubble, and I believe it's a Hubble volume. Okay, so anyway, this is our thermal tunneling rate. The third step now, after we've done all this thermal field theory, is to actually figure out how to make baryons in these expanding bubbles. So here is okay. I've got this cartoon. I've got this cartoon in my notes. Here's an expanding bubble wall. It's expanding out in this direction with speed VW. On this side, I've got the broken phase, phi non-zero. On this side is a plasma of symmetric phase. And the way we're going to make baryons is through interactions near the bubble wall. So you can think of having quarks or leptons, or stuff beyond the standard model, scattering with the bubble wall. And by scattering with the bubble wall, they can generate non-zero charges. So for now, I'll just call this some charge density QA. And if you make the right kinds of charge densities QA, the sphalerons come along, and they convert the QA charges into a B charge. And then the bubble wall comes along and sweeps up the B charge into the inside of the bubble where the sphalerons are turned off. So remember, outside of the bubble, my sphaleron rate goes like t to the fourth. Inside the bubble, my sphaleron rate is proportional to e to the minus e sphaleron divided by the temperature. And this means that sphalerons can be fast outside the bubbles and very, very slow inside the bubbles, such that they're effectively turned off. So this is a cartoon of how electroweak baryogenesis works. I've gone to all this trouble to actually get to the bubble wall and figure out when it nucleates. Now I actually want to make the baryon charges. Now I should say that calculating this stuff is a mess. It's a serious mess. There are all kinds of theoretical uncertainties and theoretical challenges. And these come about for a lot of reasons. Not least among them is that we're looking at a thermal system very, very far from equilibrium. So as the bubble passes through, even though I might be very close to equilibrium here and very close to equilibrium here, as the bubble passes through, I have a radical change in a very short amount of time. And this represents a really, really strong departure from thermodynamic equilibrium. So let me draw a cartoon of the bubble wall, kind of zoomed in.
What should characterize the velocity of the bubble wall?
So this is another challenging. This is another challenging thing.
I'm worried about it being like highly relativistic and these standard model particles can't really get.
Yeah. So actually, this is a challenge. This is actually an extra challenge for these tree level driven transitions. Not so much of an issue for the loop level driven transitions. But basically what happens is there's a pressure difference. So the pressure difference driving the bubble wall forward. On the other hand, the bubble wall hits all kinds of stuff. And so I have particles reflecting, and so it's smashing along through the plasma, and it feels a drag force. It feels a frictional force. And eventually you hit a steady state where the frictional force matches the pressure, and you end up asymptoting to some constant velocity. Now, actually, I'm not going to talk about that, but that's another part of the calculation that people often sort of don't actually do that one ought to really do.
So somehow the matter density surrounding it?
Well, the matter density plus how strongly it interacts with the bubble wall. So, this is yet another calculation you have to do far from equilibrium. It's yet another challenge. But okay, I'll say a few words about this later, but roughly we're going to have in mind VW on the order of kind of 0.1 units of the speed of light. Yes?
So are we just assuming that the temperature is like cooling with the universe, or is this like on the outside? On the outside, are we heating this up as the bubble expands?
Okay, yes, another good question. Yeah, so very often the temperature at which you nucleate the bubbles in a serious way is very close to the critical temperature. So in that case, you don't supercool for a long time. And in that limit, the temperatures are basically all about the same, inside and outside the bubble. There is a possibility that you have serious supercooling, where you sit at the origin for a long, long time. And again, this is an issue if you have a tree level driven potential. You sit at the origin for a long, long time where things cool off a whole lot, way below the critical temperature, and then you nucleate. And in that limit, you can have a serious reheating. So I'm going to have in mind the case where you don't supercool a whole lot, and my nucleation temperature is pretty close to the critical temperature. And this is, in fact, is why the phi c over Tc condition is used to characterize the strength of the phase transition, whereas a better characterization would actually be phi over T at the nucleation temperature. It just so happens that for stuff that works that we know of, it's usually the case that the nucleation temperature is close to the critical temperature. So we sort of identify them, even though this isn't always true. Okay, so getting back to this, here's my cartoon of what's going on within the bubble wall in field space along the x direction. So I'm going to assume that the bubble is essentially of a big radius, so I don't have to worry about its curvature, and it's expanding along, and it's traveling along in the x direction. So what my bubble profile looks like is over here, I have some value of the global minimum field value at the nucleation temperature, and it's constant for a while, but then it transitions to 0 outside the bubble. So I'm going to call it kind of this middle part, the center of the bubble. And this region here is called the bubble width. So this is a cartoon of my bubble. This is inside the bubble. This is outside the bubble. and this front is expanding, is traveling forward at speed v. So this is what my field space profile looks like. And in principle, you would calculate the field space profile from the profile of the bounce solution found relative for the thermal tunneling. So this is also something you can get out of Cosmo transitions. In practice, people often just parameterize this as a hyperbolic tangent, in the sense that we often take phi of z to be phi over n over 2, 1 minus hyperbolic tangent of z over LW, where LW characterizes the width of this. This is a hyperbolic tangent. So okay, it looks like this, just shift it up. And the z coordinate is x minus VWT. So the z coordinate is the co-moving coordinate relative to the bubble wall. So in other words, let's say I'm sitting out, let's say I have some random point x here. The z coordinate is the distance from the bubble wall front to this point. And then the distance to the bubble wall is VWT. So the total x from here, from this point to the origin of my x space, is going to be VWT plus z. So if I just rearrange this, my z is x minus VWT. So the z coordinate is just a co-moving coordinate that tells you how far you are from the front of the bubble wall. So this bubble wall profile only depends on, well, the effective distance from the bubble wall, the z, and we're going to just parameterize it by this form. Okay. Okay, so at this point, we want to make baryons. And to make baryons, we need to do a few things. We have our bubble wall profile. We now want to compute charge densities in front of the bubble wall, because these charge densities in front of the bubble wall are going to be the things that can bias the sphalerons to make more baryons than antibaryons, and this is what I want at the end of the day. So to figure this out, we need to figure out how the effective sphaleron transition rate depends on having background fermion densities. So before, when I wrote down the sphaleron transition rate, I didn't worry about having some background fermion densities, but I know that in equilibrium, for example, if I have a non-zero B minus L charge, the sphalerons don't completely wash that out. And I also know that the sphalerons rate, or I also know that if I have non-zero charges that aren't B, the sphalerons shouldn't get rid of them entirely. And we can take that into account by looking at how the sphalerons transition rate changes with fermion charge backgrounds, just using very, very basic thermodynamic principles. So the great thing about thermodynamics is that the input assumptions are very minimal, aside from possibly equilibrium or close to equilibrium. And the upshot of that is you can more or less apply them anywhere. So the thermodynamic principle we're going to apply here is one called detail balance. And detail balance, in the context of equilibrium, is that suppose I have two different configurations with different free energies. I'm going to tend to want to live more in the configuration with a lower free energy than the other one, but my full thermal state is going to have lots of different configurations contributing. But in principle, for a system at equilibrium, even though things are interacting and I might have transitions from one state to another, the net rate of transitions from one state to the other, if I look at the number going forward, this should be matched by the number going back. And suppose I have two states with free energies that I call F plus and F minus. This requirement that I keep essentially a time-independent occupation number within the various states translates into the ratio of the transition rates, where I go from one configuration, the lower configuration to the higher configuration, or the higher configuration to the lower configuration. The equilibrium condition, based on detail balance, is that this ratio of the rates should go like e to the minus delta f over t. And this is based on very, very general thermodynamic principles. I think relations of this sort sometimes go by the name of fluctuation dissipation relations, but don't quote me on that. Okay, but in any case, this applies to generic interactions, but we can apply them to sphalerons, and the rate at which they change baryon number. So specifically, let's apply this ratio of rates to sphalerons, where the sphalerons transitions can either increase the Chern-Simons number or decrease it. But every time I increase the Chern-Simons number, I increase the fermion density by 3 units. And each time I do it in the other direction, I decrease it. So the rate of change of my baryon number is going to be the NG of 3 units times the rate of sphalerons transitions that go up 1 unit of NCS minus the rate of sphalerons transitions that go down by 1 unit. And this is the number of 3 generations. So this is my rate of transitions. And I can rewrite this as NG times gamma minus 1 minus gamma minus over gamma plus. Oops, sorry, I wanted to write. Okay, actually, okay, so it's the same thing. Sorry, this should be gamma plus over gamma minus. And I take this, I plug this in, rearrange it here, and what I get is minus NG 1 minus e to the minus delta f over t, where delta f is a free energy difference between these 2 fermion states. And now to get this thing, though, I use the fact that my free energy difference is going to look something like the sum over all the particles in my system mu delta n, where delta n is the change in the number of particles, and mu is my chemical potential. So this is just the contribution of number densities to the free energy. So I take this, I plug it in here for the result for baryons to get my delta F. I expand this, assuming delta F over T is very small. And I've identified gamma minus as being very similar to gamma plus, and identify gamma minus as just a regular sphalerons rate per unit energy, sorry, per unit volume. And this thing turns out to be, going back to my usual thing, and I take into account the stuff that's going on for the sphalerons. This thing just corresponds to the sphalerons changing Q by 3 units and L number by 1 unit. So I'm just using the change in free energy. So this relation tells me what the sphalerons transitions do to the rate of change of the baryon density. Question? Yeah, so this is detailed balance. So that's precisely detailed balance, in that if I have a state with a slightly lower free energy, I'll have more occupation. And if I have a state with a slightly higher free energy, I'll have less occupation. But that means that to balance the rate going back and forth, I have to have a higher rate from high to low than low to high, because the total rate is kind of occupation number times absolute rate. Yeah, well, so this relation holds either in equilibrium or very close to it. So specifically, we're going to apply this relation primarily outside the bubble. It's kind of away from the bubble wall, where equilibrium is a good approximation. But what we're getting from this is, in fact, a description of a departure from equilibrium. So specifically, we're using this relation that's motivated by either being close to equilibrium, or either equilibrium or close to it. And we're putting it into a relation that tells us how things deviate away from equilibrium. Okay. About half an hour. Okay. Okay, so I look at this combination, and this combination of things is different from the combination that makes baryon number. So this combination of charges is not the same combination of charges that makes baryon number. Remember our net baryon number density, and this is the number density of baryons minus the number density of antibaryons. Remember that we define this as mu b T squared over 6 in the limit of a small chemical potential relative to the temperature, where this mu b for baryons is a sum over 3 generations, 2 mu qi plus mu ui plus mu di. So the point is that this combination of chemical potentials, if I rewrite it in terms of number densities, doesn't quite coincide with the baryon density. And this is going to be important. So this means that I can take this combination of chemical potentials, and I can rewrite it in terms of a number density of baryons plus another term. So in other words, my dnb dt can be written in the following general form, where to do better than this, you actually have to look at specific reactions that are in equilibrium. How do I want to write this? Okay. Oh, actually, sorry. There should be a 1 over t here. So I can rewrite this relation as in the following form. Is that right? Okay, actually, I can just do it this way. So what I've done is I've taken this combination of chemical potentials, I've taken this combination of chemical potentials, and I split it into a combination of chemical potentials that correspond to the baryon number density that you'll recall is different from this combination of chemical potentials. And then I've dumped all the stuff that's in here that's not in NB into these other terms. So this is a sum over some other chemical potentials that don't quite correspond to the baryon number density, with some coefficients A and some effective rate given by the Weeks-Fowler rate. So I've just done a rearrangement. I haven't been specific about doing this rearrangement because I'm also going to have to look at relations between different independent chemical potentials from reactions in the plasma. But the thing I'm going to do next is compute what this combination of charges is given the set of reactions that are in equilibrium or at least close to equilibrium in the plasma in front of and behind the bubble walls. So the next thing I need to do is compute this. But before I can go and compute this, let's just think about the general structure of this equation. So suppose that when I turn on reactions within the plasma, in front of or behind the bubble wall, suppose that when I turn on these interactions, the sum of these chemical potentials with the appropriate coefficients ends up vanishing. What this says is that if this term vanishes because of other reactions that, let's say, equilibrate charges, what I'm going to be left with is dnb dt is equal to essentially some rate times the number density of baryons. So if I don't have this term, all that this equation tells me is that my baryon density just relaxes to 0. So if I have if I start with a non-zero baryon density, when I ignore this piece just relaxes it to 0. So this piece is called a washout term. So this is a piece that in some sense is not very nice because I don't want to get rid of baryon numbers, I want to make baryons. But having said that, if I look at this piece, if this piece is non-zero, it acts as a source. So if there exist combinations of charges that when I add them up in the appropriate way, taking into account the various reactions that are in equilibrium in front of the bubble wall, such that this combination of charges is non-zero, this acts as a source, and my equilibrium state is now no longer going to be NB equals 0, it's going to be some non-zero NB, and this is what I want to get. So my next challenge is to actually compute various number density charges in front of the bubble wall and plug them into this and use this to figure out my final baryon density. But it's going to turn out that if I was just in pure equilibrium, you can show that if I'm just sitting in equilibrium, this combination of charges ends up going to 0 if I'm in equilibrium. So to get a non-zero contribution here, I'm going to have to look at this not just sitting at one point. I'm going to have to look at the effect of the bubble wall zipping through, CP violating scattering, generating contributions to this, and then looking at this as something that's non-zero only in a little region close to the bubble wall. So this is my next challenge to do. I want to compute this as a function of z. So this piece is going to be non-zero only is going to be potentially non-zero only very close to the bubble wall, and it's going to be generated by the departure from equilibrium and CP violation generated by the bubble wall zipping through. So that's the next thing I need to do. So okay, let me say that this whole thing is a huge mess to compute. So I'm just going to sketch out how it works, but bear with me. Okay, so I haven't had a chance to type all this up. So the way we compute these charges is essentially using diffusion equations. So there are all kinds of great, thermodynamics is really great. You can derive these diffusion equations at a number of different levels. I'm just going to write them down, but you can actually derive them either in a WKB approximation or in a something that follows from thermal effective field theory. I'm just going to write down the result in sort of a motivated way. So specifically, I want to compute these combinations mu a over t, and let me remind you that in general, a number density asymmetry for let's say species A, Na minus Na bar, is related at high temperatures and small chemical potentials to the chemical potential by this relation, provided. So if I have some particle species A, its number density asymmetry in equilibrium, or at least close to equilibrium, is given by this relation. So I wrote this down the other day. You can derive it by taking the difference between distribution functions. And okay, for bosons there's an extra factor of 2, but I won't worry about that. Now this combination of Na minus Na bar corresponds to the charge density, the charge density operator I would define for the A species. So in other words, I have some charge density that I'm going to write as JA0 as the zero component of a 4 vector, where the zero component is the number density asymmetry, and the spatial component is the spatial component is the essentially the flow of that particle number. So the kinetic equations are going to come in. In that the rate of change in the number density, and this is the kinetic equation part, is going to be the spatial current of that number charge plus what I'm going to call a collision term plus what I'm going to call a source term. So this piece should be fairly obvious. This is just the change in the number density of the A particle from it flowing out of a given region. This piece corresponds to the change from collisions and reactions. And this piece is what I'm going to call a source for the A species. So the way to think of these is, okay, this is the rate of change of my number density asymmetry. This is the change because it's flowing away. This piece comes from stuff like stuff in the plasma where, let's say, my A particle scatters with something else and turns into some other particle. So this piece is going to correspond to inelastic collisions. And finally, the source here in this context is going to be the source from CP violation in the bubble wall that can generate a net charge for Q. So correspondingly, a net non-zero A number charge density. So this is my this is effectively a kinetic equation, and a further approximation we're going to make is called the diffusion approximation. So the diffusion approximation is that there exists some constant such that JA is some constant D times the gradient of the charge of the number density. So this is my current, and I'm saying that my current is equal to the gradient of the number density up to some constant. So what we're going to do is, or at least do it in principle, is you compute the source of A, and you compute this as a function of the distance from the bubble wall Z. You compute the collision term as a function of the bubble wall Z, and we're going to convert this the t and x dependence here by assuming that my g0 of A is a function, and this is physically motivated, is a function specifically of Z, where the Z coordinate is the co-moving coordinate relative to the bubble wall. So in other words, the number density for any species is only going to depend on the distance from the bubble wall. And the idea here is if I'm way out here, I shouldn't care about the bubble. If I'm way over here, I shouldn't care about the bubble. But as the bubble goes through, stuff's going to change a whole lot. And this is where the spatial dependence is going to come in. So this is essentially just a statement that I'm in equilibrium except for close to the bubble wall. So this is nice because I take this form and I plug it in here. And you'll recognize this as a so-called diffusion equation. And I take this and plug it in here, and now I can relate my time derivative to my spatial derivative through this dependence on the combination of x and t. So what you get, and this is going to get kind of hairy, I'm going to rewrite these J equations in terms of what are effectively mu A over T. I'm going to call it xi A. Yes?
Isn't there another, I think I thought that there was another term in this, and a minus, and a part that does not have a temperature dependence.
So this is the leading term for the asymmetry. So the asymmetry should go to 0 as the chemical potential goes to 0. Now this is formally an expansion in mu over T, and this is the leading non-zero term in that expansion mu over T. And it's always going to be a safe approximation that mu over T is a tiny number. So it's sufficient to just work out this linear order. Okay, so remember, the thing we want to compute are these mu A's, which I can normalize to temperature to get something dimensionless. And I can take these equations, absorb these factors, and just rewrite this diffusion equation as an equation for the chemical potentials. So what you get, taking into account all this, let me try to get this right. D double prime. So I can recast my kinetic equation. Now my dt hitting the current is going to give me a power of minus v. My gradient, plugging in this approximation, this gradient is going to become a grad squared. But now a grad squared of x just gives me 2 derivatives. Now 2 derivatives in this case with respect to z. So the prime is a d dz. Here I get 2 derivatives plus my diffusion constant d. And at this point, I plug in my sources, and I'll come back to the source, and I plug in my collision term. And when I plug all this stuff in, I get I can solve this as a fairly straightforward differential equation with these sources. So for example, in the limit where the collision term just ends up being z independent, there's a straightforward solution. And let me write this down. So I'm going to write this as these equations end up being coupled differential equations for lots of different densities, because in general these collision terms are going to relate the chemical potentials of a lot of different particle types that are involved in reactions. But if you solve enough of them, often they either linearize, or I'll just look at the special case where it ends up being proportional to the chemical potential itself. So the result of all this is where are we? My psi a of z just ends up corresponding to what's essentially a Green's function solution, where the Green's function solution solves the differential equation with this simplified collision term. So if I forget this piece and just solve the simplified thing, I can derive a Green's function for it. And the Green's function is for the homogeneous part, and then I add it to the source. So the form of the form of the Green's function solution is just some diffusion thing, which I'm running out of space, but my Green's function as a function of z with a bubble wall and some assumptions on the structure of the source. Okay. Okay, so this precise form doesn't matter so much, but what you see, what you get effectively is something with exponential suppression on each side that falls away from where your source is, and it depends on this combination of parameters. So in a lot of cases, this extra thing is kind of small compared to 1, so I get either VWD on one side for k plus, and on the other side I get something that looks like 2 gamma d over VW, and this describes the fall off going away from the source. So this result is just a standard diffusion source, diffusion result that things tend to spread away. So I have a source term and then this kind of spreading away function. And this tells me that my density is going to be given by some source thing plus some spreading thing away from it. So this tells me how diffusion moves charges away from the sources for them. So my sources are going to be typically non-zero only in the bubble walls. And diffusion is going to allow them to spread away from the sources through this exponential dependence. So roughly, for example, suppose my source looks like this. The diffusion is going to let it spread out here to give me my final psi of z density. So, for example, for your standard delta function source, the Green's function lets you spread out away from the source and smooth it out. So ultimately, what we're going to get through diffusion is some charge density for psi kind of out here, thanks to diffusion from the source within the bubble wall. So the last piece of the puzzle is, okay, so this is kind of messy. The last piece of the puzzle, though, is computing these source terms. And the source terms themselves are a serious pain to compute. So let me just illustrate with one particular case that in some sense is a particular case that's probably been studied the most, which is the MSSM, minimal supersymmetric standard model. So this is officially rolled out on the phase transition side, but it's still interesting to look at for how it generates the baryon asymmetry. So in the MSSM, it turns out that the most useful charge densities, the most useful sort of particle types are the Higgs, the right-handed top quark, and the left-handed quark doublet. So these are the things that talk most strongly to the Higgs, and correspondingly, they talk most strongly to the bubble wall through the top Yukawa, and they interact with each other through the top Yukawa coupling, which is order 1. So when I write H and UC and QC in supersymmetry, we tend to assume that particles in the superpartners are equilibrated with each other, and we just lump those into single charge densities. So the charge density means particle plus its superpartner. So in this case, the Higgs means the actual Higgs, but also the Higgsinos. So if I look at the Higgsinos, the mass matrix for the Higgsinos with CP violation has the following form. It has a Gaugino mass, it has a Higgsino mass, and I can choose to put a phase here. And then it has off-diagonal mixing terms that depend through gauge couplings on the Higgs background value. And this mass matrix, which has a built-in CP violation in it, corresponding to a relative phase between the mu term and the Gaugino masses, this mass matrix is going to change as I go through the bubble wall because I'm turning on and off the phi values. So if I turn off the Higgs expectation value, I have pure Gaugino and pure Higgsino states. Whereas as a bubble comes along, I'm going to mix the Gauginos and the Higgsinos in such a way that I can also get CP violation through this phase. So what I compute is something that looks effectively like I look at something that looks like a Higgsino charge density, which corresponds to something that looks like Higgsino gamma mu Higgsino. And in the vicinity of a bubble wall, my charge density operator looks like an insertion of essentially an incoming Higgsino state and outgoing Higgsino state. And I can connect this up through a loop with an intermediate Gaugino. So actually, I'll write this as either a Bino or Wino. And then this vertex corresponds to a Higgs vertex. And the Higgs vertex this Higgs vertex can, when I have the bubble wall go through, can attach to different points, different space-time points, different z points as my bubble wall goes through. And it turns out to be the combination of this CP violating phase plus this CP violating phase plus this non-trivial space-time dependence, such that when I compute, for example, d mu, j mu, I get a correction that goes like the imaginary part of m12 times mu times something that looks like a spatial derivative of the Higgs background field, schematically. So this expression, which gives me a source, which I identify as the source for the Higgsino, this expression depends on CP violation. So this is the CP violation. And this piece is the non-equilibrium piece. And that I need this changing bubble wall profile to give me a non-zero Higgsino source. So if my new source of CP violation within the MSSM, for example, comes in through this kind of phase, the interactions with the bubble wall generate primarily, at least initially, a Higgs-Eno density. So I take my Higgs-Eno density, and I reprocess it through the top Yukawa coupling. So I have an interaction that looks like top Yukawa coupling Q dot H U3C, and that means that if I dump in some Higgs or Higgs-Eno density, so actually this should ultimately be a Higgs-Eno. If I dump in some okay, so I'm remembering this is a superpotential operator. If I dump in some Higgs-Eno density or Higgs density, this will be shared with the up and down quarks. So this looks like, in superfield notation, this looks like a Q U3C. So if I have a net Higgs-Eno density, I can transfer it to some Q density and some anti-up density through these interactions. So what this looks like schematically is, suppose I generate a non-zero Higgs density, like this, from these Higgs-Eno sources, where this direction corresponds to a particle density, and this direction corresponds to an anti-particle density. This reaction is going to take this, and through the top Yukawa coupling, is going to turn it into a Q density and an equal and opposite right-handed up quark density. So the top Yukawa coupling has reprocessed the Higgs density into some left-handed quark density and some right-handed quark density, or I should say right-handed anti-right-handed quark density, and these are equal and opposite, in the sense that at this stage the Yukawa coupling hasn't violated baryon number at all. So I still have a zero net baryon number, but I've just separated the charge into a net left-handed bit and a net anti-right-handed bit. So the next step is the sphalerons come along, and the sphalerons act essentially only on this piece, but they don't touch this piece. So what I get from the sphalerons is they come along, they eat into some of the Q density and get rid of it, and now after the sphalerons have acted, I get a net baryon number charge. So ultimately, I take my diffusion equations, I take this source, I plug the source into the diffusion equations, I add in all the reactions that change one kind of charge to the other. I go back to my master equation before, and ultimately the charges I generate, in this case a combination of Higgs charges and Q and U3 charges, when that combination of charges is non-zero, I get a net baryon number. Yes?
In a different equation before for baryon number, you had to watch out term, which also baryon number.
Yes.
These A terms, so that the Higgs density has to be bigger than that to overcome this washout.
Yeah. So
How does this get bigger than NB?
okay. Well, so ultimately I go back to my dMB dt, which actually now becomes a. I also have to worry about diffusion of baryon number, so I stick in a term that goes like d grad squared NB. So this just tells me how my baryon number moves around. And then I've got a plus something that looks like sum on A psi A. And then I have a minus something that goes like NB. So this something, first of all, is it's only non-zero. So I have rates here, and these rates are only non-zero outside of the bubble walls. So my diffusion is going to help because the diffusion is going to take some of my density outside the bubble wall, move it inside where this is now zero. But the other thing is, if this is non-zero and this is non-zero, and let's say I forget about diffusion for a second, the equilibrium point in my differential equation isn't going to be NB equals to 0. It's going to be NB equals something else if I have other independent charges that are non-zero. So just because I have a washout doesn't mean that I necessarily get zero baryon number because I have a source term. On the other hand, if I only have this non-zero in a particular region, so if these charges are only non-zero in a particular region, as I move outside of the region where I have those charges, this washout term kicks in and washes out what I have. So you should think of this as roughly kind of an equilibrium value of the number density locally when I have these charges. So what happens locally when I have these non-zero charges is NB gets driven to NB equilibrium. But this only happens within a little region in front of the bubble wall. As I move away from there, this piece goes to 0, and my B equilibrium goes to 0, and I'm done. And that gives me the ultimate washout. But fortunately, if everything goes well, I get non-zero charges in front of the wall, the baryons diffuse inside, at which point the prefactor rate here goes to 0, and I don't have any more washout, and I have baryons and us. So I think I heard the bell ring. I better finish up, but I'm around for lunch and this afternoon if you have questions, and thanks.